morning, good afternoon, good evening for everyone. Okay, my name is Zhongyi Ho. I'm the professor of the Chinese University of Hong Kong, and I'm also the distinguished lecture manager of IEEE CEDA. Okay, so it's my great pleasure to introduce our first virtual distinguished lecture series. Okay, the first speaker is the Professor Sudeep Pasricha. Okay, so before I introduce Sudeep, Professor Pasricha, I would like to mention that for this year, we have 4 new distinguished lectures. The first lecture will be virtual distinguished lecture will be offered by Professor Pasricha, and in May, the talk will be provided by Professor Ricardo Reis, okay, from Brazil, and he will talk about physical design, automation of transistor network. And in July, the talk will be offered by my super colleague, Professor Bei Yu, and Professor Yu will offer a talk on large language model in EDA. And I believe in September, we will have the virtual DL talk by the Professor Alberto Boscio, okay, from Italy, and he will talk about the AI hardware accelerator for safety critical applications. Okay, so this year we have a 4 virtual distinguished lecture talk. Okay, so for the first speaker, Professor Pasricha, let me introduce him. Okay, Professor Pasricha, he received the bachelor degree in electronics and communication engineering from Delhi Institute of Technology in 2000, and his PhD in computer science from UC Irvine in 2008. He then joined the Colorado State University in 2008, and where he is currently an Aaron and Helga Buddha endowed professor in the Department of Electrical and Computer Engineering and Department of Computer Science. And currently, he is also the chair of the computer engineering. So his research focused on the design and the application of innovative software algorithms, particularly AI and machine learning, hardware architectures, and hardware software co-design techniques for energy efficient fault tolerance, real-time, and secure computing. He has co-authored 7 books, multiple patents, and published more than 300 research articles in peer-reviewed journals and conferences, workshops, and books. His research has been recognized with several awards, including the Air Force OSR Young Investigator Award, Google Outstanding Research Faculty Award, and IEEE Computer Society CVLSI Mid-Career Research Achievement Award, and the IEEE TCSC Awards for Excellence for a Mid-Career Researcher. He is a fellow of the IEEE and a distinguished member of ACM. And as I mentioned, he is now our IEEE CEDA distinguished lecturer and also an ACM distinguished speaker. Okay, so welcome, Sudeep, please.
Thank you, Shangyi, for this very kind introduction. It's a pleasure to be here. And so today my talk is going to focus on realizing artificial intelligence at the speed of light. So I think most of us are familiar with the challenges with technology scaling today. So technology scaling is slowing down. We are seeing that it's becoming more expensive to fabricate chips, and also the performance gains that we are getting are really just growing almost sublinearly. At the same time, if you look at the application space, application performance demands are growing much more rapidly, super linearly, in fact, almost exponentially. And so today, we have this growing gap between our application demands and the hardware capabilities that can support them. So there's a lot of talk, a lot of debate about maybe Moore's law is dead, and now we have to figure out alternatives. I would say Moore's law is still alive, and the way that we are keeping it alive is by doing things like increasing the amount of silicon and how we define what a chip is. So today we are developing these 2.5D chip architectures that include multiple chiplets, tens of chiplets in some cases, and they're, of course, much larger. We are also, at the other extreme end, we have these massive wafer scale chips, in other words, where we essentially have chips the size of an entire wafer. And what this does is this increasing silicon footprint allows us to keep on integrating more and more transistors on this new type of a chip. Now, unfortunately, as we enlarge silicon in these types of chips, electrical signals become an even bigger bottleneck than they already were. So electrical signals attenuate as the distance over which they traverse increases. And so realistically, in these sort of architectures, we can only support nearest neighbor communication. So the links need to be short, and they need to be separated by some buffers or routers. But unfortunately, what that does is that any signal that's going from any source to a destination now needs to go through multiple stages. And that leads to increased latency. So we're seeing a plateauing of the performance that we can get with electronic network on chip architectures. So today, it's clear that we need new solutions that can overcome these bottlenecks with electrical communication. And that brings me to photonics. So over the last 50 years or so, we have been gradually transitioning away from electronic domain communication and electrical interconnects, and now moving towards photonics. Back in the 1980s, we sort of started moving away from large coaxial cables over thousands of kilometers in the telecom domain, replacing them with optical fibers. In the 1990s, we saw in the datacom domain, we saw entire campuses and large enterprises, again, move away from these coaxial cables and replace them with optical fibers. And then over the last 2 decades or so, there's been an increasing push to miniaturize these interconnects. And so now we are trying to, in fact, we have successfully connected many facilities, supercomputers, data centers, racks in those facilities with optical fibers. And we are also, over the last decade or so, increasingly interested in seeing how we can integrate optical interconnects at the chip scale, at the board level, or even within a chip. So in my group, we've been working on developing optical network on chip architectures for almost 2 decades now. So some of the earliest work from our group came out in the mid to late 2000s. And so since then, we've been developing different optical network architectures, different topologies, protocols for flow control, arbitration, and so on. And so this is absolutely an area of great interest to me and also to many in the research community. We've even prototyped several chips. So this is one of the earliest chips that was prototyped together with our collaborators at CSU. This, as you can see, is a clock tree, an H tree, and we essentially wanted to see how this sort of a clock tree would work if implemented with optical interconnects. So this is some of the early work that we did in collaboration with Broadcom at with CSU. Now, today, there's, again, a lot of interest in optical communication at smaller scales, particularly as we start thinking about AI. And there are these startups that are coming up, particularly interested in trying to utilize light to do more and more. And so this company, Light Intelligence, for example, has proposed this architecture to connect their compute cores. This is an optical broadcast network. In fact, it's quite similar to the architectures that we proposed in the mid to late 2000s, which, the topology, the protocols are quite similar. So it's actually good to see that a lot of those ideas are now starting to see the light of day. There's also other companies like Light Matter, which are proposing passive interposers that are supportive of optical communication. Which is also another way that we can overcome the bottlenecks with these 2.5D chips. And we are also quite interested in trying to improve communication efficiency for these 2.5D chips. And so in our lab, we've been looking at how could we develop more sophisticated active silicon photonic interposers. We've come up with new reconfigurable topologies that can allow us to connect chiplets together efficiently. And they're reconfigurable to allow for saving laser power, and which is a major concern. And we've shown some promising results, but of course, active interposers are a bit more complex, but they also open up a lot more opportunities. Now, around the 2010, 2020 time period, when there was a lot of excitement about deep learning, in our group, we were also quite interested to support deep learning workloads. And so we've been developing these sort of architectures, as I've shown here, that allow us to accelerate communication for big data, machine learning, neural network type of workloads. We developed these architectures. We showed that some of these heterogeneous architectures have really promising results compared to some of the homogeneous architectures that we had proposed earlier. But around this time, we also started to think about whether we could do a bit more than just communicate in the photonics domain. So we recognized that one of the biggest bottlenecks with these sort of architectures relates to the conversion process between the electronic and the photonic domain. So every time we use a DAC, every time we use an ADC, there is a conversion overhead. And photonics, of course, is squarely in the analog domain, right? So, but unfortunately, our processing, our storage is still in the electronic domain. So this sort of conversion is a significant bottleneck in these sort of systems. But we also recognize that data from the real world is often analog, right? And so a lot of the outputs from sensors that we take in, for example, vision sensors, is analog information. And so we started to think about, could we actually do a little bit more in the analog domain? And so that brought us to this realization that we could. And in fact, there was other researchers who were working on this problem of trying to perform computation in the optical domain. In fact, this area is quite old, but what we were interested in is trying to do this computation at a miniaturized scale, at the chip scale. So past efforts in optical computation really look at tabletop setups, which are pretty massive. You cannot really think about compact representations when you're using diffraction optics and so on. But we were interested in trying to do integrated optics-based computing. So it turns out that silicon photonics has been maturing for the last several decades, and we've been able to design very sophisticated integrated photonics components. And so now it is possible to perform fundamental operations like matrix spectral multiplications, summations, nonlinear activations, batch norms, and so on, with integrated photonic components like guided lasers, Mach-Zehnder interferometers, microring resonators, photodetectors, and in a manner that is CMOS-compatible, which means that we can actually utilize our existing fabs to be able to fabricate a lot of these devices, which is important because that reduces the inertia towards adoption of these sort of approaches. So here's just a quick look at the different ways in which an input optical signal can be transformed by various types of devices in this integrated photonic domain and effectively induce operations like multiplications and summations. So broadly speaking, at the chip scale, two approaches are popular to perform computation with light signals. The first approach relates to using controlled coherent interference principles of light. And generally what is done in this sort of an approach is we make use of a single wavelength and we rely on electrical field phase manipulation using devices like Mach-Zehnder interferometers that have these phase shifters. And using this controlled interference of this wavelength of light, we can induce operations like multiplications in the photonic domain. And in fact, this is the approach that these startups, many startups are actually using. So this is Light Matter's chip that was released or at least showcased at Hot Chips several years ago. But what we've found is that these chips, these sort of approaches are susceptible to some issues. So in fact, we've characterized some of these issues. We found that there's a lot of scalability issues. There's challenges with phase encoding noise, phase error accumulation, especially as the sizes of these arrays of MZIs increase to support larger and larger neural networks. And so there are some fundamental scalability limitations of this approach. The second approach relates to doing controlled non-coherent interaction with multiple wavelengths of light. And in this approach, what we try to do is we manipulate the amplitude or intensity of the optical signals, and we make use of multiple wavelengths. And so the nice thing about this approach is that the fundamental devices that we are making use of are much smaller than with the coherent approach, orders of magnitude more miniaturized. And these approaches also can benefit from wavelength division multiplexing. We can actually use multiple wavelengths to support computation. And so there's greater parallelism, more scalability, and a general more compact representation. So we believe that this approach is a very promising approach as we think about scalable AI acceleration. So very briefly, I want to just introduce some of the fundamental components that are required for this ecosystem. Of course, we need a laser. So the fundamental carrier of information is light that comes out of a laser. It's no longer electrons like in metallic interconnects. This laser can be off-chip or it could be on-chip. Our waveguides are typically built using CMOS-friendly materials, silicon dioxide. Using principles of total internal reflection, we can ensure that the signal gets confined to a small region and gets routed from a particular location to another. We also make use of these devices called microring resonators, these circular loop waveguides. These are very essential to perform modulation, which is just a way of talking about how we can imprint vectors of zeros and ones that we need to communicate or compute with into the light domain. So these devices help us imprint these values onto optical signals. And then we have our DAC arrays that are used to convert parameters, for example, in neural networks for tuning these MRs. And then we have photodetectors that at the destination can detect and collect the optical signals and convert them into electrical signals. And then we have these ADCs that convert the analog signals into the digital domain. So these are, at a very high level, some of the fundamental components that we make use of. Now, non-coherent computing in this manner is very promising, but there are many, many challenges with it. So one of the most fundamental challenges that we have encountered is the fact that these microring resonator devices, these loop waveguides that are used for modulation, detection, they are very susceptible to resonance shifts. So these are actually wavelength selective devices. They work typically with one wavelength. And unfortunately, because of fabrication process variations or even changes in temperature, the resonant wavelength, the wavelength that a particular MR is supposed to work with, there is a shift in that wavelength. And that's not a good thing, because if there is this shift, now the MR cannot actually work with the intended wavelength. And so this is problematic. And in fact, there are some very complex effects of things like temperature, of how Q factor changes with temperature and variations, which I've shown here, but I'm not going to go into a lot of detail. But it's a very complex problem. And we really need to ensure that these shifts do not induce this sort of a wavelength shift. We have to sort of correct for it, which has overheads. Another challenge with these sort of platforms is crosstalk noise. So now crosstalk is something that occurs in this optical domain when signals from different wavelengths interfere with each other. We call this heterodyne crosstalk. This is also visualized here, where in your spectrum of different wavelengths, you can see that there is an overlap of the pass bands, which leads to a reduction in the signal to noise ratio. And that's problematic. And we can actually, unfortunately, also have the same wavelength interfere with itself in the time domain. So the same, for example, the red wavelength in the past, since it could actually couple and it could destructively interfere or interfere in other ways with the same red wavelength signal later in time. So that's called homodyne crosstalk. And that is also yet another challenge. Very, very hard to overcome these challenges. But we can. It just costs us power. And so if we are willing to increase our power consumption, we can make our system more reliable. But these are things that we need to carefully look at in how to try to optimize more efficiently. And then lastly, the optical signals in this ecosystem are propagating not through vacuum, but they're propagating through silicon dioxide waveguides. And this is a material that is not perfect. And so what that means is that your optical signal also attenuates to some extent. And so photons get dispersed, and you do end up having some signal loss. And in order to compensate for this, again, one way to do it is just to increase the laser power, but that has a high power cost penalty. So to try and overcome some of these fundamental challenges, we firmly believe that these non-coherent architectures are more scalable. And so the way that we can actually move towards realization of these architectures in the real world is to slowly start addressing the many challenges, including some that I've just mentioned. So we've been developing over the last few years these accelerators for AI workloads using non-coherent silicon photonics. We've been developing architectures for many different types of neural networks, which you should be able to recognize here. What I'm going to do next is just to give you a few examples to show you the ways in which we are developing these architectures and also the challenges that we face and how we are trying to overcome them. So let me start by talking about CNNs and DNNs, which are quite popular. They were the sort of seed for this whole deep learning revolution. In our lab, we develop a lot of these architectures, neural network architectures, particularly for projects in our lab that relate to perception in autonomous vehicles. And so we've been working on the domain of autonomous vehicle perception for quite some time now. And so we've been developing 2D, 3D object detectors that rely very heavily on these CNNs and also just your fully connected DNN layers. And so several years ago at DAC, we presented this cross-slide architecture. This is called cross-slide because we perform optimizations at multiple layers or in a cross-layer manner. So we perform optimizations at the device level, we perform optimizations at the circuit level and the architecture and OS levels. So let's look at the device level. So at the device level, our goal was to develop these microring resonator devices, very important devices for this type of platform, so that they are resilient to fabrication process variations. So we explored, for example, in this figure, what I'm showing is our exploration of changing the waveguide width of the ring waveguide and also the input waveguide. So going from left to right, we're increasing the width. And what we found was that as we increase the width of these waveguides, the resonant wavelength shift slope reduces. This is just another way of talking about the susceptibility to fabrication process variation. So in other words, by increasing width, we are actually becoming less susceptible to fabrication process variations, which is also intuitive because as you make the device a little bit bigger, small changes with fabrication don't have as much of an impact. And thickness, we were not able to vary because of the platform that we were fabricating this on. But at least we saw this sort of nice trend in terms of the susceptibility reduction. Unfortunately, when our width increases, it also has a negative side effect, which is it reduces the crossover coupling of our device. And crossover coupling, if it reduces, it leads to more errors when we try to couple signals from the input waveguide to the ring waveguide. So for error-free operation, this is not a good thing. So we need to do something about it. So we started to think about unconventional ways of designing these microring resonators. So one approach that was quite promising that we found was to increase the width of this ring waveguide in proportion to the width of the input waveguide, which we did not change. So we found that if we did this, what would happen is as we changed the width, we increased the width, it allowed us to still improve our susceptibility or reduce our susceptibility to process variations, but it allowed us to find these sweet spots where our crossover coupling was at a high enough value that it could still lead to significant benefits and in terms of susceptibility, and then also still allowing us to get error-free communication and modulation with these sort of devices. So this is just a quick snapshot of some of the work that we did at the device level. And we fabricated these devices to validate them in collaboration with CLAT. Then at the circuit level, one level up, what was important in these sort of platforms is to come up with circuits that can help us tune these microring resonator devices so that even if there is a shift in the resonance wavelength of these devices, we can actually compensate for that. So whether it's thermal, whether it's for a fabrication process variation, these tuning circuits will help us get us back on track and get these devices working properly. And today, there are two approaches to do this. The first is thermo-optic tuning. The second is electro-optic tuning. Thermo-optic tuning essentially uses very tiny built-in heaters in the vicinity of these microring resonators, which, as by virtue of increasing the temperature, it can induce a change in the refractive index of these devices, and it can help us compensate for these resonance wavelength shifts. Electro-optic tuning also allows us to compensate in a similar way, but instead of heating, it is reliant on charge carrier injection. Now, these two approaches are well known. Unfortunately, they have some trade-offs, which makes each of them by themselves not particularly optimal for tuning. For example, the thermo-optic tuning approach is incredibly slow because it relies on changes in temperature locally, which can take microseconds of time, which is too slow. Electro-optic tuning is much faster, and it can tune very quickly. Unfortunately, electro-optic tuning also has a much smaller range. In other words, it can only compensate for very small shifts in the resonance wavelength. Thermo-optic tuning can compensate for larger shifts in the wavelength. So we were in a dilemma. We wanted to come up with a circuit that could have the beneficial properties of both of these approaches. And so we actually created a hybrid approach. So we combined both of these electro-optic, thermo-optic approaches. And the general high-level idea here is that we wanted to make use of electro-optic tuning as much as possible because it was faster. And a lot of times it was sufficient to compensate for resonant wavelength shifts. But occasionally, we also needed to make use of thermo-optic tuning to compensate for larger shifts. So using this TED approach, we were able to come up with a way to be able to balance both thermo-optic tuning and electro-optic tuning in a way that allowed us to minimize thermal crosstalk. And then these circuits, we also were, we needed to figure out how they would actually be laid out. And so we explored ideal layouts, the designs for individual MRs, but then also how do we create banks of these MRs that can then allow us to integrate them into larger architectures that can allow us to perform optical computation. So we did a lot of analyses relating to that. And then one level up at the architecture level, we developed our optical compute engine. So this is the optical compute engine. It, of course, needed reliance on DACs and ADCs to communicate with an electronic control unit that would orchestrate operations with these integrated optics devices. But then also we need the electronic domain because all our information, all our activations or our parameters are actually stored in digital memory. So just looking at the optical substrate, we decided to create separate sub-engines for convolution operations and fully connected operations. And the reason for that is that the order of the vector dot products that need to be done is quite different across convolution layers and fully connected layers when we implement it in the optical domain. So we certainly can still just use a single array. You can call it a photonic tensor unit, and it can basically do vector multiplications. But we found that it is a lot more energy efficient and a lot more efficient, again, from a latency perspective, to have separate engines for these two different types of operations. We also did quite a bit of work on trying to creatively reduce the laser power for both of these sub-engines. And then here's a look at some results from this effort. So we, for our analyses, we just looked at 4 neural networks, CNNs. And of course, we're working in the analog domain, so precision is a challenge. And how many bits of precision we can get is of course, it's not going to be the same as in the digital domain. But fortunately, applications like the ones that I've shown here are amenable to quantization. So we can actually reduce the bit width of the parameters down to 16, or even if we go down, say, to 8, you can see that the reduction in accuracy is fairly minimal. And so there are at least certain applications that are okay with being quantized. And so these are applications that can work well in the analog domain. We performed quite a bit of architectural exploration, design space exploration, to determine the exact dimensions of the vector dot product units in both the conv layer and the fully connected layer sub-engines. And so this slide just shows the trade-offs between different alternatives. This FPS is frames per second, essentially a proxy for performance. EPB is energy per bit. And then we're also interested in keeping area overhead low. And then what I've shown here is the optimal solution, which is basically just the solution with the best ratio of frame per second to energy per bit. And so here's a look at the different architectures we compared again. So we looked at various electronic domain accelerators, also a couple of optical accelerators that had been proposed up to that point. And so the first result I'm showing is that of power. And so our architecture, we estimated it to have a power of around 75 watts, which actually is not lower than some of the state-of-the-art efforts. State-of-the-art efforts actually have much lower power. And so we're not really the greatest in terms of power consumption. But compared to the other optical computing architectures, we showed that we could get significant reductions in energy per bit. And then keeping the same metric, in terms of energy per bit, we actually are better. We are lower compared to all platforms. And then when we look at performance per watt, the metric that we use is kilo frames per second per watt. Again, the optics platform provides us with a lot higher performance per watt. So these are promising initial results that indicate that there is potential for this approach to get better energy efficiency and better overall performance. So subsequently, we were interested in seeing how these architectures would scale up. And so we created a 2.5D implementation of this platform. What I'm showing here is for several neural network models, the latency and the energy per bit for 3 different configurations. So Crosslight is just the monolithic chip-based implementation. The next implementation that we attempted was a 2.5D implementation, but with an electronic chip scale network or network on interposer. Unfortunately, if you look at the average bars, you can see that this particular implementation is actually much worse than the monolithic implementation. That's because of the challenges with electrical signal attenuation at that scale, which I talked about earlier. So the last configuration that we explored was one where we made use of optical interconnects to connect the different chiplets, and we found notable benefits in being able to do that. So next, I want to also very quickly talk about RNNs. So sequence learning is an important problem. Today, a lot of problems relate to doing things like time series prediction. And so these LSTMs, GRUs are widely used for lightweight sequence learning. In fact, today we can also use transformers, but they're much more heavyweight. So in our lab, we've used these RNNs for things like anomaly detection, particularly in networks of vehicles. And so the challenge with trying to accelerate RNNs is that the fundamental GRU or LSTM cell is much more complex than sort of the basic components of CNNs and DNNs. So now we need to create these MAC arrays or VDP arrays, which are a bit more complex in their fundamental units. So in this work from a few years ago, we did attempt to do that. And so some of the innovations here that we explored, in addition to what we did with Crosslight, relate to having these integrated memristor cells that can allow us to reduce the energy of tuning the microring resonator devices, and then also trying to perform operations relating to nonlinear activation functions using devices like SOAs in the optical domain, so that we have to, again, rely less on going to the electronic domain. We also did quite a bit of design automation and exploration for the fundamental devices, again, to try to make them even more robust to process variations. And so our analyses across several state-of-the-art LSTM and GRU accelerators with different technologies, some on FPGA, some custom ASICs, indicated again that this optical approach can be quite promising for accelerating sequence learning type of tasks. And then, so the last example I want to give is transformers, which are at the heart of all large language models today in one form or the other. In our lab, we've been very interested in using these transformers on mobile edge platforms, in particular for an application that we've been working on for quite some time, which is indoor navigation. So we want to enable the sort of indoor real-time navigation like in this figure that you're seeing on the right of this slide. So the challenge with transformers is that they are perhaps the most complex neural networks out there compared to CNNs, RNNs. They are way more complex. And so a few years ago, we proposed the first optical accelerator for transformer neural networks. And the challenge that we had was to design efficient units to be able to accelerate the multi-head attention layers, and then also couple it efficiently with all of the other layers that exist in both the encoder and the decoder. So again, we relied on principles of cross-layer design. So we extensively explored the fundamental building blocks for this sort of a transformer architecture. So what I've shown here in this figure is us exploring the Q factor of the different devices, basically their selectivity, the channel spacing for the spectrum of wavelengths that we are using, and then also looking at the radius of the devices and its impact on signal-to-noise ratio. We want it to be as high as possible, and so we are trying to select the best possible option out of the many possible options when designing these devices. We did the same sort of analyses, but at an architecture level, coming up with different ways in which we can arrange our building blocks, and again, tried to find an optimal configuration which had the lowest ratio of EPB to GOPS. So we analyzed this approach, this architecture on several different transformer model variants. And again, we found some very promising results in terms of both energy per bit and just raw performance compared to the state of the art. Now, if you think about the dominant computing platform today, it's no longer desktops or laptops, right? So today it is indeed IoT or embedded devices. And in fact, we are seeing an almost exponential growth in these other devices. So why am I talking about that? Because at some point we realized, okay, if we want to spread these platforms out to the maximum possible compute devices, we really now need to start thinking about how could we implement these accelerators in the context of these embedded and IoT devices. So that's when we started to think about, okay, how could we integrate these accelerators into edge devices? And very quickly, we realized that edge computing, of course, has a lot of constraints. And one of the biggest constraints for our purpose relates to power consumption. At the edge, we really cannot be dissipating a huge amount of power. We cannot be close to 100 watts in terms of power dissipation. In fact, our power needs to be maybe 10 watts or even less. And if you're talking about IoT devices, it really needs to be less than a watt, right? Which is a significant challenge with optical platforms because they do require power-hungry tuning and lasers. And so that was something that we started to now think about. And so over the past few years, what we've been doing is coming up with these architectures on which we perform hardware-software co-design to attempt to make them more amenable to implementation in the edge computing domain. So let me give you an example. So this is the Sonic architecture, which we presented at ASP.DAC a few years ago. And so the idea here is we are relying on sparsification or pruning in different ways. And we are actually trying to perform hardware-software co-design in this work, and that's what we did, to try and sparsify our neural networks, maintain accuracy, while at the same time intelligently changing the design of our vector dot product units so that we can work with sparse vectors and dense vectors, which is more complex than it sounds. And so the sparsity of our architecture allowed us to get some significant benefits, particularly for power consumption. And so this is just a look at energy per bit. For our Sonic architecture, I've also shown Crosslight and several other architectures. So what we found is that sparsification can allow us to get more than 10x reduction in our EPB values compared to crosslight, which is us moving in the right direction for potential edge implementation. Another approach that can be used is to make use of quantization. So in fact, if we go all the way to the extreme scenario, we can essentially come up with binary neural networks. But of course, binary neural networks, as many studies have shown, do sacrifice for accuracy. And so in order to preserve accuracy, oftentimes it's important to keep the activations at a higher bit width. And so in our work, we also recognize, and you can see it here, if the activation bit width goes down to really small values, we can see a significant drop in accuracy for certain applications. So we can still use binary weights, but maybe not activations. And so this is the sort of very lightweight, hyper-quantized model type that we wanted to accelerate. And of course, it's intuitive that having these sort of lightweight models can reduce the burden on the hardware. And so in our work from a few years ago, we proposed the Robin architecture that is essentially designed to optimize these types of neural networks. We had to re-architect our baseline cross-light architecture in many different ways to support this sort of quantization. We also added a few more innovations. We implemented operations like batch normalization within the photonic domain. We created a new data flow pipeline. Our architecture is a bit different than cross-light. And so with all of these innovations, what we were able to accomplish is a significant reduction in power, again, compared to the baseline cross-light architecture. Okay, so in this last part of my talk, what I want to talk about is what's next. What are the more interesting open challenges in this domain? And I would say there's a lot of opportunities for very interesting research that exist. So the first thing that I would say is an interesting challenge is working with foundation models. So we are all familiar with these massive foundation models that may have trillions of parameters. Unfortunately, that's basically pushing our accelerators in the electronic domain to their breaking point, and it's obviously going to have the same effect on photonic accelerators. So our photonic AI accelerators, we've shown that they can have a reasonable acceleration for neural networks that have millions of parameters, potentially getting up to billion, but trillion is a significant challenge. So how do we design photonic accelerators for these massive foundation models remains an open challenge. Another issue that is important to address is training. So all the accelerators that I've shown you are inference accelerators, but there's also a desire to support training in the optical domain. Unfortunately, that's not straightforward. Training requires bidirectional flow of information, particularly when we make use of stochastic gradient descent and backpropagation. And so supporting this sort of bidirectional information transfer with the same devices, same waveguides is very challenging. We can absolutely duplicate this entire effort, create a forward pass implementation, backward pass implementation, but that's a significant overhead. So we would like to reuse the same devices for both directions of this flow, but that's fraught with a lot of challenges. There's a lot of interference of signals that are propagating in different directions. And also we want to be able to support rapid updates of parameters, which can also be quite challenging. So this remains pretty much an open problem today. Another very interesting open challenge is, could we combine photonics with some other emerging post-Moore technology? So today there's, for example, a lot of interest in using these memristive crossbars to also accelerate neural networks. So is there a way, and in fact, does it even make sense to combine these new technologies together? So it turns out that there could be some interesting things that can be done in this space. As just one example, this work from our group from a few years ago integrated multiple arrays of memristive crossbars together with optical interconnects. So essentially, we're not doing computation in the optical domain here, but at least we are able to perform very quick transfers of information, of massive amounts of information between crossbar arrays. So there could be some very interesting hybrid architectures with different technologies that could be explored. Another challenge relates to the analog to digital and digital to analog convergence, which now that we are sending information with light, now that we are computing with light, to a large extent, we have been able to reduce some of these conversions. However, one major bottleneck still remains, and that is the interactions with memory. Memory is still in the electronic domain, and it does require a lot of these conversions, particularly for our large neural network models, where we need to get and update a lot of information. So can we do something about it is an open challenge. And it's something that we've started to look at. How could we access and store data photonically? And so some of our work from last year at DATE looked at how could we design main memory architectures that are accessible using optical signals. So this is a very interesting challenge. It's very much an open challenge. This is our first attempt at trying to address this. And it again required a pretty significant effort at multiple levels of our design stack. So we needed to, in fact, starting from selecting the type of material that we want to use for our cells. So we actually relied on phase change materials, PCMs, as our fundamental storage material. But it turns out that you can use light signals to program these PCM cells and also read from these cells. So the traditional way of accessing PCM cells is electronically, but we can also do it photonically. So we did in this work an exploration of the types of materials that make sense for this PCM. How do you design a PCM that is in the vicinity of these waveguides that are carrying optical signals? So we came up with these designs, again, using a lot of algorithmic design space exploration. And then we had to build this fundamental cell where these microring resonators really are akin to the sort of access transistors that we have in our, for example, in DRAM, when we're trying to access our data from a capacitor. So in a similar way, these microring resonators allow us to access information from this PCM cell, but do it optically. And we can also update with a higher power laser the actual value, so we can change the state from amorphous to crystalline and back. And so using this fundamental cell that we built, we created these subarrays, very similar to how we have subarrays inside our other memories, but this time it's all built with these fundamental cells. And then these subarrays allow us to build larger arrays. They allow us to build banks, and then these banks together allow us to build an entire memory architecture. So in this work, we explored how do we do that. And then the nice thing about this sort of memory architecture is that if we now use this memory architecture that's optically accessible with an optical compute engine and with optical interconnects, it can allow us to reduce frequent analog to digital to analog conversions. So this figure I've shown, there was a transformer accelerator that we modeled. And the Comet architecture, which is our architecture, you can see that it has much lower energy per bit for the two variants of these architectures compared to basically several other state-of-the-art approaches for main memory systems. So again, this is still an open problem. This is just me showing you our first attempt to try and build a photonically accessible memory, but I'm sure there's many other better ways to do it. Now that we're talking about photonic memory, I guess the natural question becomes, okay, could we reduce data movement in this sort of an ecosystem even further? And one intuitive way to do that is to just compute inside memory. So another open sort of challenge today is, could we develop good in-memory compute architectures that are photonic friendly? And so our work at ES Week last year looked at how could we take this Comet architecture that I just talked about, and how could we now extend it to support computations within the memory structures, which is quite challenging because of many, many reasons. Again, the paper has a lot of details, but in order to simultaneously support reads and writes from memory banks while also supporting computation within certain subarrays requires significant design creativity to be able to ensure that we are not wasting laser power and we are supporting high levels of parallelism. So again, this is very much an open problem today. Another challenge that is largely unexplored today relates to security of these silicon photonic accelerators. So it turns out, and what I've shown here is just a very simple example of a few microring resonators that are used to imprint activation values. Then these microring resonators, we imprint the weights, and the interfered signals actually allow us to perform multiplication in the optical domain. All it takes is one hardware Trojan to slightly impact the tuning circuit for one of the microring resonators. And now what ends up happening is you have this sort of cascading effect, and it can have a significant problem for, create significant problems for your computation, significantly degrading accuracy. We can also have other ways in which we can induce attacks. And so in this work from actually work that I will present in a few weeks at date, we actually looked at how we could have some thermal hotspot-driven shifts in resonant wavelength that are hard to compensate for very quickly. And they can again induce significant errors in the computations that we are trying to do. So this figure just gives you an idea of how, as we increase the amount of microring resonators that are attacked with different mechanisms, how the accuracy of resonant 18 degrades. Even for a very small number of MRs, you can have a very significant reduction in accuracy. So in the paper, we also discuss techniques that can help us robustify these models. And so how could we create more secure silicon photonic accelerators was one of the things that we were trying to do in this work. Okay, so I will say that if anyone is interested in learning a little bit more about how we can support deep learning, AI with silicon photonics, there is a very nice survey that we put together a few years ago, which should be a good introduction. If you're trying to come up with new ideas for research, or if you're just interested to know what's going on in this domain, this survey is a good starting point. So let me wrap up. So just a couple of concluding thoughts. So I would say that integrated optical networking and computing is an exciting new area. There's a lot of open problems. Our recent work just shows how optical computing can benefit AI. It can help accelerate AI, and it has very, very interesting benefits in terms of scalability, performance, energy efficiency. And in fact, there's a lot of startups that are emerging that are focusing on chip scale optical computing and networking. So this, again, is a very interesting area. It's an interesting career path for those of you who are looking for directions in terms of what sort of a career you want to have. So I would end by saying that the future of photonics is bright, no pun intended. Quickly, just a couple of acknowledgements, many funding agencies that have supported the work that we've done. I want to acknowledge, of course, all of the graduate and undergraduate students that have worked with me on a lot of these projects, and my collaborators in both industry and academia. So with that, I'm at the end of my talk. Thank you very much for your attention.
Okay, thank you, Sudeep. It's very informative talk. Yeah, you talk about, you found the fundamental of this optical NOC, okay, the device, the challenges, and then talk about several applications for AI, yeah, even for the foundation model, even for the security, okay. I think you pretty much cover all the things. Yeah, so very, very impressive. Yeah, thank you. So any questions from the audience? So if you have any question, please type your questions in the Q&A box. Okay, and then the Sudeep will look at it. Okay, so before that, I have a few questions. Okay, the first question is about yeah, because you talk about this optical and the optical silicon photonic chip. Okay, yeah, I think recently I look at several researchers. Okay, working on the kind of different directions. Okay, because I think your talk is more like people talking about more and more and more, right? So your work is more like more and more because you are using this for several applications for AI and etc. Yeah, so how about the large scale silicon photonics? Can you comment on this? Yeah, because when I look at your talk, I I think maybe I missed something. I'm not sure currently, because currently I remember there are many researchers working on this large scale, okay, silicon photonics. So can you briefly comment on this direction? Okay.
Yeah, so when you say large scale, are you talking about sort of beyond the chip or supporting a lot more computations within the chip scale?
The second one, support
Okay,
more.
yeah, so okay, so now that relates to scalability, and that is indeed one of any sort of post-mode technology. This is one of the most fundamental challenges that we face. How do we scale up? So several things that I want to say about it. So in my talk, I talked about how fundamentally we are trying to think about scalability from the ground up, and so that's the reason why, even though we have done research on both coherent, non-coherent architectures, our emphasis is shifting more and more towards these non-coherent architectures that make use of much more compact microring resonator devices than, say, MZIs that are much bigger. So we're trying to sort of, from that level, trying to think about scalability and starting with what we think is the right set of building blocks. Then, of course, the challenge becomes how do we sort of support massive, for example, neural networks, right, in these substrates. And so one challenge that still is a fundamental challenge that we are trying to address, and many others are trying to address as well, relates to the density of these devices. So these devices are, compared to a transistor today, they're pretty large, right? And so clearly the performance per area is an important metric. And so there, photonics has some limitations because some of the devices are pretty massive. However, the ways that we are trying to address this is the fact that, first of all, we can multiplex multiple streams of information processing and information communication within the same waveguide. We could potentially, for example, be working with, I don't know, 20, 30, 60 wavelengths, each of which is sort of in parallel trying to do computation. Then we can have space division multiplexing where we have multiple of these resources working in parallel. So the nice thing about photonics is that within the same area, after fabrication is done, you can adapt the amount of parallelism that can be supported, and you can scale up that parallelism to, up to a certain limit, but you can certainly scale it up and scale up. So we see that as a positive with the photonic domain. And then also, if we use creative ways of die stacking and being able to stack multiple components, that can also alleviate some of the area concerns. So I would say these are sort of the standard approaches that we are looking at, but density still remains a challenge.
Okay, thank you. Yeah, I have a second question, very quick question. So can you go back to the previous slide? Yeah, so you meant
This one?
Yeah, this one. Yeah, there are many new startup companies. Does any company work on the silicon photonic accelerator? Yeah, I
Yeah.
just
So I showed you that one example with light matter. So they in fact they have this sort of coherent photonic accelerator. So they have these MZI arrays that are and they showed this, by the way, 4 years ago at Hot Chips. And so since then, there's a lot of these companies that are trying to come up with prototypes. So, but again, there is no, Light Matter has built these servers that have the next generation of these accelerators, but there's a few companies that are doing this.
Okay. Okay, thank you. Yeah, I will take a look. Yeah, so we have one question from the audience. Yeah, it's from Jiang Yin. Okay, so Sudeep, can you look at the question?
Yeah, I'm taking a look at it just now. Give me just a moment.
Yeah.
Yeah, so this is a very good question. So the question is essentially asking, when you're designing or analyzing optical network topologies, are there any quantitative methods or models that allow for a quick system level evaluation of key parameters like bandwidth, crosstalk, insertion loss? Because most of the current approaches seem to rely on very detailed device level simulations or measurements that then are scaled up. Yeah, so I think this is very much an open problem today. So there are not a lot of open tools available. In fact, my collaborators and I, we have some tools that do things like crosstalk analyses, loss analyses, but we don't have like a full stack tool that we have released yet, although we have internally some tools that we work with. Unfortunately, we don't have like a push button tool where we could, for example, explore across the stack a lot of these metrics, but it would be nice to have. And so this is one of those things that if we had more time, more student effort, we absolutely would love to create this. Unfortunately, all of us are resource constrained, so we have some limitations there. But I do see that this is an important requirement for this area to grow. I think it's important. I mean, in fact, EDA has always flourished whenever we have easier accessibility to tools. And so I would say that this would be a very important requirement to come up with a tool like this. And so then we can build more efficient architectures going forward. So a wonderful question. I don't have a great answer to give you for that in the sense that we don't have those tools yet, but I hope we can all work together as a community and develop those.
Yeah, that means we have many open problems to go on. Yeah, so that's a very fascinating area. Great. Okay. So any further question? So if not, I think we already spent 1 hour here, and note that this talk will be recorded. Yeah, so I think normally it take 1 or 2 days, then we will put the recorded video on the CEDA presentation library on YouTube. Okay. Yeah, so once again, thank you, Sudeep, for the wonderful talk. Yeah, I really learned a lot. Really appreciate it.
It's my pleasure. And I want to thank CEDA for giving me the opportunity to give this talk.
Thank you. Thank you. Okay, so thank you for coming to this talk. And also, yeah, thanks of Sudeep for the wonderful talk. Thank you. Okay,
Thank you.
bye-bye.
Bye.